The first speaker this afternoon is Maria Schonbek, who will talk about decay characterization of solutions to dissipative systems.
Thank you. First of all, I would like to thank the organizers, especially Elena and Milton. In particular, Elena, because she has invited the Porteña, which was very amazing to me. Well, anyway. This is an inside joke between Brazilians and Argentinians. Okay, what I want to talk is about some very, very recent work. We just finished it with Cesar Nietzsche on what we call the decay characterization of solutions to dissipative equations. So essentially what we found was that every time that you work with certain type of dissipative equations, you in some fashion redo many things because there's no organization. So we're trying to figure out what produces the decay. And essentially what we say is that the decay is really given in, you take the initial data and you look what happens near the origins in the Fourier space, and that's going to define the characterization. And that's what I want to explain here. So that was the introduction. I'll give this characterization of the initial data. I'll describe how the linear part works, and then I'll go into some applications, the Quasi-Geostrophic equations, approximations for the compressible Navier-Stokes equation. The Navier-Stokes equation also falls into it, but that's results which are a little bit older, as I will explain later on. So let me just say what kind of dissipative systems we want. We want dissipative systems where we can ensure that there is this kind of energy inequality, which obviously Navier-Stokes has. It turns out that the approximation for Navier-Stokes work with that. Geostrophic equation doesn't have exactly this, but when I put an inequality of this type, what I mean is here it could be a power alpha, and it could have more, a little bit more, but this is essentially the basic thing. And what we're going to do is try to describe the behavior of the datum near the origin in frequency space and see how that influences the decay. And the goal essentially is to find both lower and upper bounds of the decay rates. And the lower bounds are more complicated, and I'll explain where we get stuck. The upper bounds are in general much easier. And the main tools is going to be this decay character, which I'm going to define, and what I call the Fourier splitting method. So obviously, equations which work in this category will be the Navier-Stokes equations, MHD, certain compressible systems, Boussinesque, and the geostrophics. Okay, so let me start again with this. We know for Navier-Stokes that we have this kind of inequality. Well, it's an equality if you have a regular solution. It will be an inequality if it is the weak solution. If we work with weak solutions, we can always use approximations. All these methods, you can do them on approximations and then pass to the limit. So what is the problem here? So there were the obvious questions. The first question was as everybody knows, was asked by Leray in his 1934 paper. There's a nota bene at the end asking what happens with the L2 energy. And Kato did answer this when you had small data, but with small data, as we all know, the linear part has the advantage, and so it's easier. But the first answer to this problem was given by Masuda in 1984, where he simply gets a rate without decay. So the second, then I did something about L1, L2, and we get the decay rate that you want, which is the same as for the heat equation. Then, moreover, you realize that what Masuda does is exactly the best thing you can do when you only have L2, because you take a ball of the same radius, and you can show that for each t, you will always find something which doesn't go as fast as you want. So in other words, there's no uniform rate. And then Wigner got something slightly better. So in other words, he got that the decay was between an alpha, if you have the linear decay, then the decay was was decided by either the linear part or at most it could be minus 5/4. And in that case, for instance, the case when you have an initial mass 0, you get the minus 5/4. And then you could do something with initial data, with higher derivatives. So essentially what happened here is we did this for Navier-Stokes. The question is, can we do all of this for all these dissipative equations? And so you go back and you say, okay, what did determine this decay? And the idea is that the low frequencies will do it. And using what I call Fourier splitting method, you get all the other decays. But the question is, how can we do it for everything so that it's something more standardized? So here's a this picture well, it's the obvious picture. I just want to write it down here, do it here. So what we have is 3 situations. We look at the frequencies near the origin. So if I take the Fourier transform of the data, then I have there 3 situations. One where we have, this is all 0. The second one is when this object is of order c to the power k, and the third one is of this case. And in that situation, you can show very easily that you will have exponential decay here, a decay of order, so it would be minus n over 4 plus k over 2, and here it would be minus n over 4, where n would be the dimension of the space where you're working. And here we are working on the whole space, so we don't have Poincaré. So essentially the easiest way to look at this is if you go to the heat equation, and there it can be done very easily because the solution can be written out as the convolution of the heat kernel with the initial data. If you pass to Fourier transform, you see immediately that if this is equal to 0, you have exponential decay. From here, you have the decay rate that I had mentioned before. And then if you are in this case, if you are in L1, L2, you get immediately a decay rate of minus n over 4. Okay, so this is, I want to get rid of this because it's too elementary for this crowd. Okay, so let's go to what I really want to do, what we did with Cesar. So essentially, there was a result that I had before with one of my students, Clayton Bjorland, and Cesar was insisting that this could be generalized, so that's what we tried to do. So we look at the low frequencies, as I say, and we look at what happens with the linear equation. Those 2 things are going to characterize our work now. So let me introduce couple other things. So then once we have the linear part, we go to the nonlinear part, and then in order to study the lower bounds, we need to study the difference between the linear and the nonlinear. So the first thing I want to do is define what we call the decay indicator. So if you take the initial data and you take a small ball around the origin of radius rho, and then you multiply it by rho to the power minus 2r minus n, and you let the rho go to 0, that's what we define as the decay indicator. Essentially what this does is to take this initial data u sub 0 in frequency space and compare it with the function c to the power r near the origin. So this is what we believe, and that's essentially what we are doing here. So this is the comparison that we have. I mean, this is essentially what we believe is giving us the decay. So that was we did that we defined this with Bjorland, and then we redefined it with Nietzsche, but I'll explain what's the difference with the new definition. And once we have that, you look at what we call the decay character. So what we're looking for is a number, one number, which we call R star. And that number, if you look at this, I mean, there's two possibilities. Either this limit exists, and then it's unique, or it doesn't exist, and then it could be, I mean, it would be 0 or infinity. So what we call the decay character is this number, which is going to be between minus n over 2 and infinity, if it exists, and it's strictly bigger than 0 and strictly less than infinity. On the other hand, if it's infinity, we're going to say that this decay character is equal to minus n over 2, and if the decay indicator is 0, then we say that the decay character is equal to infinity. So essentially, when the decay indicator is 0, we're in this case. So essentially what happens here is that we're going to have decay as fast as you want, I mean, for all powers. So then the first extension was to say, okay, if we have a decay indicator, I mean, can we do it for derivatives? And the answer is yes, you do exactly the same thing, but now instead of comparing the Fourier transform at the origin with c to the power r, what you do is you compare the powers, depending on which derivative you want to take, with c to the power r. So that's what we call the decay indicator. And then what we do is we define the s-decay character. And this is exactly the same, only that now instead of you're going to have this value r star, there should be an r star, between minus n over 2 plus s, where s is the number of derivatives, and infinity. If it exists, so in other words, if you have such a number, you call that the s-decay character, and otherwise, if this was 0, you take as a decay character plus infinity, and if it was infinity, you take minus n over 2 plus s. Now, the decay character is not going to give you the decay. The decay rate is going to be given by this decay character plus something, and the something will be minus n over 2, multiplied by a constant which will depend on if you have diffusion, fractional diffusion, or if you have just the Laplacian. Okay, couple of remarks. One immediate question is, how do you compare, what is the connection between the decay character and when we start with an initial data between LP and L2? Obviously, you take P between 1 and 2, and what you get is that the decay character is going to be minus n times 1 minus 1 over P. So if we look at the case when you are in L1 intersection L2, then the decay character is 0. If, on the other hand, you have an initial data which is just in L2 and it doesn't stay in any of the LPs, then the decay character is minus n over 2. The decay rate, as I said, would be this object here. If you take the L2 squared, it's just going to be minus the decay character plus n over 2. And this here is going to depend on if your diffusion is Laplacian, then this is 1. If it is a fractional power, let's say power alpha, then it's 1 over alpha. Now, in the case that you are in L1, L2, then the L2 norm squared, because this is 0, is just minus n over 2. And in the case that you have no LP, then this is when you have that the decay character plus the n over 2 gives you 0, so you don't have a specific decay rate. You have a non-uniform decay rate. Okay. So the next thing that we said was, well, I mean, if we have this decay character, how do we go from the decay character that we had originally, which was just for the L2 norm, and then what happens if we connect it with the HS norms? And so what you have is that if you have the decay character for the L2 norm, you will find that the decay character for the S norms, for the HS norms, is just what you had originally plus S. And so in other words, you would have your R star minus S as your, in the ending relationship. And you have that the R star corresponding to the S indicator is S plus your original character. And then the other thing is that if you have decay of all orders for the derivatives, that's only if you have decay for all orders for your initial solution in L2. And the same thing happens if you have no decay, you will have no decay for the derivatives. So a couple of remarks. I just decided to say, well, what are the proofs? Very short, very quickly, let me say the following. If you want to show the first part, so that from the decay character in L2 you get the decay character for HS norms, you write down this expression, which is when we take the limit when rho goes to 0, this expression is going to give you the s-decay character, and this expression here gives you the decay character just directly. And you choose an appropriate R, and you play with this. Essentially, when I say you play with this, if you take the limit, you get an inequality between the decay indicators. Once you have this, you can say, okay, what does that tell you? Well, what it tells you is that if this is bigger than 0, you're done, because you can get that the s-decay character is going to be equal to q plus s, which is what you wanted, where q was the original decay character. And then you have to work a little bit harder. So if you have that this was equal to 0, you're going to have two cases. So the first case, you're going to suppose that there exists some R so that this decay indicator is strictly bigger than 0. But if that happens, then you go back to the first case and you're done. In the second case, if this is equal to, if it is equal to 0 for all larger R's, then what happens is you have, again, two cases. The first one is the same. Oh, shoot. The first one is the same as before, and the second one leads to a contradiction. It's a little bit more technical, but essentially what happens is you only have the first situation, and the first situation leads to having established what you wanted to do in number 1. Number 2 and number 3 is the same kind of idea. You just play around with your decay indicators. That gives you the decay character, and you get these conditions. Okay. Once we have this, we go back to the linear part. Now, the only linear part that I can do is cases where I have, so I'm just taking dissipative situations where we have that ddt of whatever we have here is less or equal to minus a constant times the gradient of u squared. Maybe here we have powers. But essentially, I want to have a situation like this. In order to have a situation of that type, what I'm doing is taking the linear part defined by a pseudo-differential operator, which is essentially giving you this. So in other words, you can write it out as a diagonal matrix multiplied by, which is similar to a diagonal matrix. And the diagonal matrix is of this form. So the linear equations, the linear part is going to be an equation of this type. But this equation simply means that we have our standard inequality. Once we have this, the question is, how does the decay character, what kind of a role does it play? So essentially, so this is what I just said, that you can write out, if you have a pseudo-differential operator, as I said before, then you have this inequality. And once you have this inequality, you can use what I call Fourier splitting to get the upper bounds. So let me give you a couple of examples, which are not the typical examples where you do have this kind of an inequality. So the first one would be the geostrophic equations. The second one, that isn't the completely standard one, is that if you take the compressible approximation to Stokes, in that case, you can have immediately a system of the type that we wanted. And if you make the computations, I think this is by Rusin did that, right? The next computations. You did? Oh, you did that. Okay.
I did so.
Okay. Sorry. So, so if you compute the symbol, you can write the diagonal in this fashion. The orthogonal matrix is going to be as expressed here. And then what you can do is you can write the kernel in this fashion. So this is one of the equations which looks like a little bit less standard than the one that we had, where we also can apply our results. So let me go back to the linear part. So if I have the linear part, now I go back to what I'm saying. Suppose that my decay character is of this form. So I start out with data in L2, and I have some specific decay character. Then I look at the linear part, the linear equation, and my decay character will fall into minus n over 2 and infinity, or it might be minus n over 2 or infinity. In the first case, when it is in this range, then I get the expression that I wanted for an upper limit, and I get the same kind of an expression for the lower, for my lower bounds. So how do I get this? Well, oh, I'm sorry. I forgot about this slide. So in this particular case, what we have is that when you have that your decay character is minus n over 2, then this tells you that you don't really have a lower bound. I mean, what you're saying is that your solution will decay slower than any uniform algebraic rate. If, on the other hand, it's equal to infinity, then it's going to decay at all possible rates. So this is, again, this is the case where we are over here in the last one. So let me tell you a little bit about the proofs. So back to here, we have our equation, our linear equation. We have the symbol. This is simply so that we can estimate. So essentially, this is like a Laplacian or a Laplacian to a power alpha. And how do we get the lower bound? Well, the first thing is that in this particular case, because of the R star that so in other words, the decay character that we have easily that our kernel is going to be bounded by this expression here, where rho is, you remember, you had your P of R star. This was equal to the limit when rho tends to 0 of rho to the power minus 2n minus r. So this would be 0. And here we would have the u0. And we do this over a ball of radius rho. And so, so that's where the rho comes from. And so the only thing that you have to do is you rewrite the L2 norm. This is the linear part. And so I'm multiplying by rho to the power 2r plus n and dividing it by the same thing. This expression here is the stuff that comes from the indicator. Because the indicator is bigger than 0, this expression here is bounded below by a constant. And then what you have is this product of this expression times this expression. So you end up with this expression over here. And so what I want to do is choose a rho which is convenient. And the rho that I choose is exactly the decay rate that I'm looking for. And if you notice here, if I multiply t by rho to the power 2 alpha, if I choose this as my rho t, that's going to be essentially a constant. And I get my lower bound. So the lower bound is very easy. For the upper bound, now you do a little bit of what I call Fourier splitting. So we start with our inequality. This is the one that we have from simply the being dissipative by the energy inequality. And then what I do is I can write this out. This term here, I can bound it if I take this B to be of, if my ball is of radius rho, I can, because I have a minus sign, I can pull this out and write this out as on the whole Rn. If I have it on the whole Rn, I get the L2 norm. I pass that over here, but I have one bad term, which is on the ball of radius rho, which stays here. So this is the kind of Fourier splitting that I have to do. Once I do this, now I go back to what my decay indicator was and simply start bounding this. So how do I do this? Well, I know that this, because my decay indicator was less than infinity, I know that this is bounded by a constant. And so now I take this whole part here, which is the part that we had, where do I have it? Sorry. Yeah, so what I do is I multiply this by this expression. And if I multiply this by by rho to the power minus 2r minus n, and I multiply it by rho to the power 2r plus n, then I pull this out here, and I'm left with a constant times rho to the power 2 alpha plus the 2r plus n. And that's what I have on this side. And now I choose a rho which is convenient. And what I get is, when you replace it, and you divide by rho to the power 2 alpha, that disappears, you get the rate that you want. And for this, you just choose your rho as a power of 1 plus t to the power 1 over 2 alpha. Okay, so that essentially is going to give you the upper bounds. And so what you get afterwards is you say, okay, you do the same work, but now you work a little bit harder, and you get also that the S derivatives are going to have the same kind of estimates as the L2 norm, only that now they're going to go S times faster. So the powers are going to be the power that you had for the L2 norm, and then it's plus 1 alpha times S. And on the other hand, if you are in the case that your decay character is infinity, you're going to have that this is going to decay it's going to have a decay of all orders. Okay. So what we have now is we have to go, we have the linear part, which is fixed, and so the question is, can you do this, can you work a little bit more and get the nonlinear equation? So the first one we were looking at was the Quasi-Geostrophic equation. So this is a slide which has been shown many times here. So we have the Quasi-Geostrophic equation, where we have theta is our temperature and u is the velocity, so which is obtained through the Riesz transform. It's just a standard geostrophic equation, and we have our power alpha is between 0 and 2, simply because I've put the Laplacian here. Okay, in this particular case, now we go back to our data in L2, and now we look at the decay character. In this case, we are in 2 dimensions, so n over 2 is 1, so we go from minus 1 to infinity. Our alpha goes from 0 up to 1. In the case that our decay character is it's less or equal than 1 minus alpha, and bigger, obviously, than minus 1, we get the same decay, the decay that it was expected for the linear part. In the case that you have larger decay characters, the decay that we get is slightly different. Now, so this kind of decay, in the case that you take L2 intersection L1, was something that was already in the old paper of Constantine and Wu. But in most of our proofs are going to be very similar to the proofs that Constantine and Wu had, simply that now instead of having the specific case the specific character equal in the case L2, L1, it would be equal to 0. We have a more general situation. Okay, so the usual thing is that if we want to prove this theorem, we do it in a formal way to get this to be rigorous, we do it on approximations and pass to the limit. And here the idea is the same as the usual thing. You make a Fourier splitting. So how do you do the Fourier splitting? You take a ball around the origin of a certain rate. You write this into the equation you're going to get after working out the same way as before, which is you split the ball into this ball and the complement, you're going to get an inequality of this type. Here, this is going to be the linear part. This is the part that comes from the nonlinear part. And so what you do is with the Fourier splitting, you are going to choose an f which is convenient. And the first time around when you choose the f, you take a logarithm to a certain power. You have to separate it when alpha is equal to 1 and alpha is less than 1. And if you plug this in, you're going to get plug it into this, you're going to get a decay. The decay that you get is a logarithmic decay. Once you have this, you go back and you say, well, you plug everything into this equation again, but now use that your temperature decays at this rate, and make, when you do that, you get an equation which looks pretty ugly, but it is of this form, but you can rewrite it in a very simple way. So just making a change of variables in some fashion, you introduce a function of this type, and what you get when you introduce a function of this type is an expression of this form, and you use Gromwell. This is essentially, this last part is exactly the same as Constantin and Wu used in their original paper of 90-something. I don't remember when you... 99, yeah, okay. So what we get then is, once you have that, a little bit more work will give you all the derivatives. So in other words, the nice thing is that you get that the derivatives are exactly the same as the L2 norms plus the order of the derivation. Again, upper bounds is always, first you do a Fourier splitting. And the only advantage is that because you already have the L2 norm, in this case, you don't have to go through the logarithmic decay. You can do directly get the algebraic decay. Okay. Then the next thing that you do is you say, okay, what happens with the difference between the solution and the linear part? Same kind of, in some fashion, it's the same kind of idea. You get, the only thing is that you have to be careful, depending on the decay character, depending if it is less or equal than alpha minus 1 or bigger or equal than alpha minus 1, you get different kind of decay rates. Now, in order to do this difference, the only thing you do is you write this difference, you get the differential equation, and you apply Fourier splitting. Now, what's going to happen is that you have one bad term, and this bad term is actually the term that comes from the nonlinear term. And what you have here is that the linear term is easy to estimate. You get a decay rate for this. This, you already have the decay rate. And then once you have that the nonlinear term decays of this form, then you go back to this equation, which you're going to have an equation of this type, plus a term here, but this term decays already at a certain rate. So this estimate, I mean, is exactly the same as the one that you find in Constantin and Wu's paper. And so once you have that, you just apply Fourier splitting, and you get all the rates that I had written out over here. It's mostly technical computations. Okay. Once you have that, you can say, well, what happens with the lower bounds? With the lower bounds, what happened was that we cannot get all the decay characters. The only thing that we can get is when we have the decay character first between -1 and 1. That is provided that alpha is large. And then for alpha, that's provided that alpha is less than 1/2. When alpha is bigger than 1/2, we get a second type of decay. But the thing about it is that when R star is bigger than 2 times 1 minus alpha, That's an open question. And the reason is very simple, I mean, because the proof is very simple. The proof simply means that what you do is you take this kind of reverse triangle inequality, and you have that, you can bound it from below by the linear part minus the difference between linear and nonlinear. And as long as the difference decays faster than the linear part, you're in business. And the problem is that when R star is very large, this term here starts decaying much faster than than the difference. So that part we do not know how to do it yet, but we're thinking about it. Okay, this is just in this theorem. We just put everything together. So this is just a repetition. So we have, when R star is between less than 1 minus alpha, we have the same decay as for the linear part. When we go bigger than this, here we have different decay rates for upper and lower. And when we are for larger than this, we do not have any lower decays. Okay. The nice thing about this is that when you take the Navier-Stokes equations and you look at the estimates that we have just obtained, we get exactly the same rates for the geostrophic than for the Navier-Stokes, with the only difference that our alpha in this case is equal to 1. So once we had this, we decided to see what happens with the approximation for the compressible Navier-Stokes equation. In this case, let me just remind you what that is. This is so Temam introduces this penalization method where the divergence of U is exchanged for minus e times the pressure, and then you add a stabilization terms of the form 1/2 divergence of U times U. So your equations now look like this, and so this is a compressible equation, but the thing is that because we have this stabilization term, we still get the same kind of dispersive inequality without the decay term. So in this case, what we did is we did all the computations, and what we find is the following. The first thing is, so this is our equation, this is our linear equation, this is our symbol, and we can write it in this fashion. So what we have is that the nonlinear part, the nonlinear equations are going to be in some fashion similar. We know that when we multiply by U, we will have no problem because this term is going to be cancelled by this term. And so then we tried to see what we could get, and what we had is that first, so the first thing we got was that when we stay between minus n over 2, which in this case would be minus 3/2, and 1, we have that the upper bounds are what we expect, that minus n over 2 plus the decay character, although that in this case alpha is equal to 1, so the 1 over alpha just gives you 1, and we have the same lower bounds. Now naturally when we look at our R star bigger than 1, then we only get upper bounds. The methods are the same as before. You just have to go and do the Fourier splitting for the upper bounds. For the lower bounds, what you do is you just find out what the difference is between the linear and the nonlinear part. Once you have that, you use a reverse triangle inequality and you obtain the lower decay. You work a little bit harder, you get that the derivatives have upper bounds, which is exactly what you expect. You just have S plus the value that you had for the L2 norm. And then what we did was we checked what happened with the difference between the linear and the nonlinear part. That's going to decay a little bit faster, provided you are in the right, for the right R star, and then you get the lower bounds by a triangle inequality. And I think that was all what I wanted to say, with exception of, I think this slide shouldn't be here. So yeah, I had one comment which was simply we wanted to kind of figure out how to work with all of these dissipative equations instead of going, well, if you have L2 intersection LP, or if you have just L2, we just wanted to have some kind of a characterization for all of these equations. And we essentially feel that we got it in the case that we have in the case that we want to get upper bounds, and for lower bounds, we just have it as usual whenever you know what happens with the linear part and the difference is decaying faster than the linear part, then you have you're going to get the lower bounds. On the other hand, as an open problem, it would be a nice thing to get all the lower bounds, but that I think is a pretty hard problem. And that's it.
Thank you very much.